G'day, I'm Dr. Philip Button from the Food Entrepreneurship Academy. Now, in some previous videos, I've covered elements of shelf life, preservation, and especially pH, the role of pH in food preservation. Now, in this particular video here, where I'm coming to you from beside the Yarra River in Melbourne, you can see the river behind me and the city skyline as well. I want to take you through a couple of slides on the chemistry of pH, just to put it into context, the chemistry perspective and chemistry background of what actually happens in pH control of microorganisms in the food preservation context. So I'm going to share my screen and we shall get underway. So here we are. So what I want to go through, are really these three concepts that I've got at the top here. pH in the first point, pH, acid strength, and acid concentration. So pH it's important to remember that pH is a measure of the acidity or alkalinity on a pH on a logarithmic scale or a log scale. So a pH of 5, for example, is 10 times more acid than a pH of 6. So anything at 6 or less is acid. Anything at 8 or more is alkaline, with 7 being neutral. So that's basically a indication of the hydrogen ion concentration in a given solution. So that's what pH is. It's a scale from 0 to 14, with 0 to up to 6 is in the acidic range, 7 is neutral, then 8 to 14 is alkaline. I want to just jump to acid concentration. So acid concentration is the number of molecules of a given acid in a solution. So that can be expressed on a percentage basis, or in the case of if we're talking about a real chemistry expression, then that's going to be in molarity. So the amount of acid molecules. So a 50% is a higher concentration than 10%, or a molarity of a 5 molar solution is going to be a higher concentration than a 1 molar solution if we're using chemistry terminology. So acid strength refers to strong and weak acids, and that's actually a measure of the capacity of an acid to dissociate. So only when an acid dissociates can it actually affect a change of the pH in the surrounding medium. So, or in the case of the context of what we're talking about, it's all about reducing the pH of the cytosol of bacteria, for example. And therefore, if an acid is strong, then it readily dissociates and is able to enter the bacterial cell and affect a reduction in pH. So that's the difference between strong acid, which dissociates readily and more to a higher degree, whereas weak acids have a much less degree of dissociation. And there's a relationship between strong and weak acids and organic and inorganic as well, where, by and large, more strong acids are inorganic. So we're talking about hydrochloric acid, HCl, H2SO4, for example, whereas weak acids, which have a much lower degree of dissociation, tend to be organic. So citric, malic acid, lactic acid, acetic acid, those are organic acids which have a lower degree of dissociation than their counterparts, than their strong acid, inorganic acid counterparts, and therefore have a reduced capacity really in preservation. So a reduced ability to lower the pH inside the bacterial cell and therefore lower preservation capability. Now, total titratable acidity is a concept based on a analytical chemistry procedure, which is called an acid-base titration, and that measures the concentration of acid. So it's unrelated to pH and unrelated to acid strength. So pH can be readily measured with a pH meter. Acid strength is, you can find that out through what's called the pKa of a particular acid. So that is the important element of the chemistry behind acids and bases. So the chemistry behind what pH is, what a strong and weak acid is, so acid strength, and the definition of acid concentration, and how we measure that in an acid-based titration to determine the total titratable acidity. Now, even though in theory we've got pH, acid strength, acid concentration, the actual preservation capability though is determined by the buffering capacity of the food, and that is related to the buffering of the acids that are already there as a function of the natural makeup of the food, and also any preservatives and other elements, other food ingredients really that can buffer. So, for example, milk is known to have a particularly good buffering capacity. So, meaning milk is around pH 6.6 to 6.7, and it is very difficult to change that pH because milk has a very good buffering capacity. So even if you put a lot, you have to put a lot of acid in milk to be able to reduce that pH. So these are some of the scientific considerations based on the chemistry of acids and bases that need to be taken into consideration when you're looking at how best to use pH or acidity as an intrinsic factor for food preservation. Now, I want to wrap all that up with this particular slide here on pH and microorganisms. So I've gone through elements of this in a previous slide, but this shows the effect of food pH on the growth of different types of microorganisms. So most microorganisms, of importance in food are neutrophiles, which means they grow close to the pH, the neutral pH, which is around 7 or just below, like 6.5 to 7, sometimes slightly over. Having said that, it's mainly bacteria that grow in that range. So foods that are have a pH around neutrality will tend to be spoiled quickly and will tend to be spoiled by bacteria. And by reducing the pH of those foods, we make it difficult or impossible for bacteria to grow, but we then open up the food to spoilage by fungi, so yeast and mold. So we actually select for the growth of fungi by reducing the pH. So by adding acids in there, reducing the pH, say, to 6 or to 5, or even lower to 3 or 4, we're certainly gradually reducing the capability of bacteria to grow, or eliminating by the time we get down to like pH of 3 or something. But we're increasingly selecting for the growth of yeast and molds. And so that's why you have foods like jams, yogurt, and fruits and vegetables, or especially fruits, that tend to be spoiled by molds and yeast to some extent, but it's mostly molds who grow at that low pH, whereas bacteria don't. So if we, by reducing the pH, we're eliminating or reducing the growth of bacteria, and therefore we're enabling a longer shelf life. But ultimately that food will still spoil, and it will still be spoiled, by and large, through the growth of fungi, particularly molds. So that's something important to keep under consideration that, by reducing the pH, you're just really shifting from growth of bacteria to growth of mold, and over a longer time, because mold grows slower than bacteria. Those are the two slides what I wanted to cover on the chemistry and microbiology of the use of the intrinsic food preservation mechanism, pH, in how you can preserve your food products. So thanks very much for listening. I'm Dr. Philip Button from the Food Entrepreneurship Academy, wishing you a very good day, and I look forward to seeing you again in one of our next videos, or either meeting or seeing you in person at one of our in-person events in Melbourne, or indeed elsewhere. Thanks very much. Take care, and I shall see you around. Bye.